First of all, I want to say thank you to Rodney for the introduction and to Ken and Rulon Enterprise for the invitation. And thank you guys for being our audience. I want to talk to you today and just share some of my research. Some of this stuff is preliminary. All of it is ongoing. So hopefully I do well enough to continue to break the rule about bringing professors in and to be able to come back subsequent years to talk to you. So we're going to talk about cover crops and their effect on the fate, and I don't have on there, but the availability of soil inorganic nitrogen, okay? So nitrogen management or nutrient management, nutrient loss, as you know, is a very, very hot topic, okay? It's a topic that people are passionate about, and it really involves the people that are in this room. I think last week sometime, I woke up and I was brushing my teeth, and my wife said, "I think you want to watch this." And so I came running out of the bathroom, and the CBS morning show, that was their title of one of their sessions. The Gulf of Mexico's dead zone is the largest ever recorded in history. And I said, wow, let me see what they're going to say about this. So they began to talk and discuss, and here's some of the things that the transcript said. And also NPR had an article, and it was saying that basically the dead zone is 8,776 square miles wide, surface area. And it's adding to the debate of whether the federal government is doing enough to, I guess, force farmers to stop polluting the Mississippi River Basin, which then flows to the Gulf. This is the language, okay? Farmers use those nutrients, right, on their fields as fertilizer, right? And then that fertilizer then flows to the Gulf, enriches the water, causes algae and aquatic plants to grow rapidly, so then they die. And then microbes consume those, they decompose that algae, and as they decompose that algae, they're respiring, just like we are right now. And so they're consuming oxygen. So the other aquatic wildlife, like crabs, shrimp, fish, they don't have oxygen, so they die, so they call it the dead zone, okay? This is on national TV. This is and it's coming from farmers and those nutrients, right? And they also say, and they're questioning on national TV, does voluntary measures, are they inadequate? Are they adequate? In other words, can farmers get this done themselves? Or the alternative, is the government doing enough to force farmers to get this done themselves? Is anybody concerned about this language? Raise your hand if you're concerned. All right, that's what I thought. So it's a hot topic, and this is on the first thing in the morning with CBS, the morning show, okay? And so it brings to light this nutrient loss reduction strategy that 13 of the Midwestern states that make the largest contribution of nutrients and water to the Mississippi or Chaffalaya River Basin has been required to develop in order to increase voluntary adoption of nutrient management practices and conservation practices that are best management to reduce the loss of nutrients from the field. And Indiana is one of those states, of course, okay? Illinois, all of the upper and the Mississippi River Basin states. So the target is to try to reduce phosphorus and nitrogen loss by 45% by the year 2025. That's a tough target. That's a tough target, right? And so one of the things you have to think about is, first of all, we can't do this one farmer at a time. It has to be a watershed effort where several farmers come together like this and decide that they're going to do something to change this narrative that's being played out in the media nationally and internationally about what's going on in the Gulf and how, yes, we are feeding the nation, You guys are feeding the nation. And so it requires some fertilizer. Just because the dead zone was the largest that it was on history, does that mean that all farmers are bad? No. They never mention climate change, right? Which drives just natural mineralization, which is the conversion of nitrogen from organic to inorganic, right? It goes into NH4 ammonia, then from there it nitrifies and goes into nitrate, right? I'm gonna show you some data that shows that illustrates that happens at a significant rate, even if you don't apply fertilizer. Even if you don't. So that means that soybean year, when you think, I don't have to really worry about it, you do. There's data that says that 80%, upwards to 80% of what's lost in a corn year is also lost in a soybean year, right? And so, so my research basically answers the questions, how does cover crops as a conservation practice interact with nitrogen? And how does it affect the fate and the availability of that nitrogen to subsequent crops that are planted after the cover crops? So then you have to think about nitrogen conservation, nitrogen release, and nitrogen uptake. Conservation is basically dictated by, what type of cover crop are you planting and into what type of soil. Whether that cover crop overwinters, and it talks about conservation, you have to think about the cover crop is interacting with what pools of nitrogen, right? So I talked about this natural pool where the nitrogen is mineralizing from the organic matter. Then there's a residual pool, right? That pool is the leftover nitrogen that the plant did not take up the first year, that previous year. And then there's the pool of nitrogen that's applied in the fallow period in the fall, like DAP, right? How many people apply DAP in the fall? Most do, right? And then also you have, in some states, there's fall applied anhydrous, where there's still 50% of the farmers are still fall applying anhydrous. And in other states, especially like Indiana, there's manure application. That nitrogen counts also towards what's happening in the Gulf. So how does cover crop interact with those pools of nitrogen? And then once the cover crop has interacted and assimilated that nitrogen into its system, into the stem, into the structure of the plant, like as a protein, right? Then after termination, how long does it take to get that nitrogen back? Most of the time when I talk, I'm talking in places like this, and I get, right when I'm about to be done, about 3 years ago before I started another line of research, I would get asked by some farmer that would make me want to run out of the building, because he would ask me, and he would say, Doc, you did a good job of explaining that we did get the nitrogen, stabilized temporarily, but I really want to know, when am I going to get my money back out of that plant that took up my nitrogen? And so I began to do residue management studies to try to figure out how long does it take, how much is taken up, and how long does it take to be released back to the soil solution. And now we're actually trying to track that nitrogen molecule. We'll label it, that molecule, and says we're going to watch it get taken up by the cover crop, we're going to watch it get released into the soil, then we're going to watch it get taken up by the corn or the soybean the subsequent year. And then we're trying to track it all the way to a bushel. Because if I could get to a bushel, I could get to a what? A dollar sign. And so we're trying to do that currently. All right, so this first study is work that I did before getting to Purdue, but I'm still currently doing it, so my research program is regional, okay? And so basically, I'm looking at the effects of cover crops and nitrogen application timing on nitrogen loss in subsurface drainage, okay? 3 scenarios. The first 2 are already in the nutrient loss reduction strategy. And so I wanted to basically use the guidance of that strategy and put that to test to see what will happen. So the first strategy is to change the nitrogen application from fall to spring. For some of you, this is a no-brainer. But like I said, in some states, there's still a huge portion of the nitrogen that's still being applied in the fall, which is commonly more susceptible to loss, our drainage and into the Gulf. The second thought was change the nitrogen from fall to spring, which is the first, but add cover crops to that. What happens? Okay, there's been a lot of work done on that, okay, especially in Iowa and Ohio and so forth. Then the third is something that I developed when I was a young professor 7 years ago at Illinois State in Bloomington, Illinois. And I looked at the literature and saw all of these farmers and looked at the numbers from, the numbers from NRCS and so forth, saw all of this nitrogen applied in the fall. And then I looked in the scientific literature and I said, who's looking at this and who's trying to help these farmers move from one place to the other with their management? And there was basically very little in the scientific literature. And the scientific literature was saying, do number one. The farmers were saying, half of them were doing number one, half of them were leaving that nitrogen in the fall. So I said, what happens if I increase the cropping intensity, add a cover crop to the system, and then allow farmers to fall apply into that living stand of cover crops? Will there be any interaction between the fall applied nitrogen, whether DAP, manure, or anhydrous, between the cover crop, with the cover crop? Will the cover crop interact with it and temporarily store it? And in early studies, I found with anhydrous that whenever you had anhydrous injected into a living stand of cover crops, let's say radish, cereal rye, or the mixture of the two, that's what I studied, it was more likely that in the spring, 3 weeks before planting, right at the termination of cereal rye, that you would have a greater percentage of what you injected where you injected it compared to lower depths closer to the tile drain. So we determined that over 3 years, and I'm just putting out a paper right now that's looking at that over a 5 to 6 year period. And basically we also determined that weather, climate, is affecting it. In a year where it freezes up like it used to, like normal winter, you don't get a difference. So if you inject in the fall and it freezes up like normal with N-Serve, everything is fine. That nitrogen stays where you injected it. But if it's abnormally wet and warm in the winter, when you inject without the cover crops, your plume, the highest concentrated area of nitrogen, moves closer to the tile by the time you're ready to plant. Right? That's a no-brainer. Because it's warm, microbes love that. It's wet, they need water, okay? And so you get this fast conversion of ammonium to nitrate. But when you have cover crops, that plume of nitrogen, that concentrated area where you inject, it stays concentrated where you injected it in the fall. So spring and fall, nitrogen concentration looks about the same, okay? If it's really wet in the spring, okay? And so what the pattern is that you'll get this, as you increase with depth in the soil profile, you increase the nitrogen concentration. That's not what a farmer wants to see. If he put the nitrogen 6 inches below the surface, he don't want to see it 2.5 feet down in the spring. That's not what you want to see. Even in that abnormally wet spring, cover crops keep most of that nitrogen closer to the surface. So I said, okay, we got something. Okay? It's been published, it's been proven. Let's take this and put it over tile drainage to see if that concept will translate into less loss and equal or greater yield. So that's what this test is all about. So to test these 3 scenarios, we had to look at 5 treatments. Now, this was done, and most of my work is done on a farmer's field the way farmers would do it. I kind of take pride in being applied. I take pride in farmers being able to see my methodology and say, oh yeah, I would do that, or I can do that. So you can imagine me collaborating with the farmer that has his own thought pattern on how he wants things done. And I say, well, I tell you what I need. I need a quarter of your field not to get any nitrogen, and we're not going to put cover crops. You think that went over well? No way. So that was a little struggle. And I finally broke through when I asked this one question. I said, how would you like to know how much nitrogen you're losing even if you don't apply nitrogen fertilizer? And he sat back in the pickup truck and he looked at me. He said, you can find that out? I said, I can get a good estimate of what it's going to look like. Then he said, let's do it. So I got in a breakthrough on that. The next two treatments it's a split application of nitrogen with the dominant split in the spring as anhydrous, and then 20% is as DAP. Okay, sorry. And I did that with and without cover crops. Okay? So a split application with the dominant portion of the split in the spring, with and without cover crops. Then there's a split application with the dominant portion of the nitrogen split in the fall, with and without cover crops. All treatments except number one received 200 pounds per acre of nitrogen. This is in central Illinois, in Lexington, Illinois. So when you think about the MRTN, the range, 200 pounds is right in there, okay? The cover crops used was a cereal rye radish mixture. Why? Cereal rye radish has the tendency to take off and grow well in the fall with good conditions, okay? And it scavenges at a rate higher than cereal rye early on. But then radish does not overwinter. So when it dies, let's say late December, January, and it begins to decompose immediately. You think it's not decomposing in the winter. It is. And we have data proving that it does. So it's decomposing, and cereal rye is kind of relaxing in a dormant state. And then here comes March, April, May. Cereal rye wakes up and takes off again. And I believe that there's some synergy between the two cover crops in that mix, where the nitrogen that's been released through the decomposition of the radish is also being contributed and taken up and absorbed by the cereal rye, and the cereal rye is kind of taking that nitrogen like a relay, like track, and continue to grow in the spring. Okay? So just to give you an understanding that we're able to detect surface management and how that surface management is affecting what's leaving the tile. So basically, each one of these blue squares is 1.6 acres, which is about 72 rows wide. Each square has those red lines, which are tile laterals, which are 45 feet apart, 3 of them. They converge about 15 feet before a control structure. That control structure allows us to slow the water down long enough in order to sample directly from the tile water, which is directly affected from the surface by the surface management. Okay? So this farmer, when I got there, was already like 8 to 10 years of strip till before corn, no till before soybeans, and his nitrogen management was 60-40, split of fall and nitrogen, fall and spring nitrogen application. So this yellow box, it looks like this. So basically it's an all-weather-proof box, and inside of that box is just instrumentation that allows me to automatically take water samples to measure for nitrogen directly from the tile. Now this is awesome because before this was invented, I had to have a lot of graduate students in the rain taking samples. But now this little blue box is the communication module. It starts to rain, it sends a text message. Hey, we got enough rain to flow. We're now flowing. And then 4 hours later, it'll say, hey, you need to come change the bottles. Now, that text message does not come to my phone, but it goes to my graduate student's phone. I designed it like that, okay? So I told you that we pride ourselves on doing things like farmers would do it. So how do we apply the cover crops? We basically contracted out the application, and the guy came in with a Hagen modified to drop seeds into standing corn, right? So we're not out there cranking the seed out with a broadcast spreader, okay? It was the treatments were too fine. There's not enough area to fly it on. So this was the next best thing. And we were able to get in and out of the rows of corn and soybeans, drop the cover crop seed while it was standing, and then expected growth when we were harvesting, okay? And so we did this without knocking down, I think we knocked down less than 1% of the stand. And that was amazing that he was able to get in and out, avoid my instrumentation, and because each one of those instrumentation boxes, that's $15,000, and I had 15 of them. And he could have really did some damage with this kind of equipment, but he was able to, pick up his wing, turn, pivot. It was amazing to see. So this is just a picture of some of the growth and some of the later growth, and you can see the mixture working well there. So the farmer really, I say, he prided himself on, hey, if we're going to do this, I'm going to use all of my technology. So it was a true collaboration. So we were able to kind of strip till into the living stand of cover crop with the nitrogen application here. Then in the spring, after termination, you can see the dead residue. We came back and planted right in that residue. Okay, he was doing all of that with his guidance equipment, and I was all for it, right? And so this is kind of what it looks like in soybean residue. And so here's the cover crop biomass and nitrogen uptake. Now, I know it's a lot of numbers, but we're just going to take it one row at a time and summarize. It's the biomass here, and this is the uptake here. And so you can see here in 14 and 15, we got pretty good biomass. We didn't get a lot of growth that fall because it did get cold, okay? And so you can see the associated in uptake. But then look at the difference between the fall to spring. That's why that mixture is important. If I just had radish, I would get something either equal or less than this. But because the cereal grew in the spring, I got a dynamic change and got 40 to 54 pounds per acre of nitrogen, with an average of about 48 pounds per acre of nitrogen. Okay, 15 fall, 16 spring. 15's fall was not really a fall, right? So it was very, very warm. So you can see that the difference between fall and spring is not really there. So a lot of the growth happened in the fall because there's so many growing degree days in the fall. But we still got similar total in uptake, about 54 to 56 pounds per acre with an average of 59, okay, compared to the previous cover crop year. 16 and 17 was similar to 14 and 15, okay? But we got more biomass in the spring because this time the greater percentage of growing degree days was in the spring, long spring, and plus it was wet. So we couldn't get in and plant, so we had a cash crop planted later, so we let the cover crop continue to grow a bit, okay? But look at the uptake due to that long spring. We got an average of about 77 total pounds per acre taken up and assimilated into the structure of the cover crops, which means it's organic. And we have to wait for it to be released. And if it's organic, that means it can't denitrify. Or it can't leach. So it's temporarily safe. So when you look at the average across all 3 years, cover crops was able to take up about 30% of what the farmer would apply. That's important to me because that says that we are actually affecting mass-wise, on a mass-to-mass basis, we're affecting about 30% of the application, okay, over a 3-year average. So one question that always comes up when you add cover crops to a system is how does it affect the volume of water leaving the tile? Is there any effect? And what we saw was a seasonal effect. So whenever you had cover crops growing, you can see here that cover crops were reducing the amount of water leaving the tile. So that means there's going to be an impact of the load. There are 2 ways you can affect nutrient loss. Either you can keep the nutrients in place, or you can reduce the amount of water that's leaving the field. Cover crops were doing both in this particular location, okay? This is one of my favorites, okay? So we started this 10/2/14, and the last data point that I have that's current is 5/19/2017, okay? So a pretty good stretch of time. And here's what we come out with as far as cumulative loss that's leaving a tile, nitrogen load that's leaving a tile, cumulative, over the entire span of the project. So if you look at the green circle is spring with cover crops, the black is spring without, the green triangle is spring, so you really can't see that, but just the green is where you have cover crops, okay? And so when you look at the breakdown, when you compare a farmer that says, I'm gonna move my nitrogen from fall to spring, or I'm gonna leave my nitrogen in the fall, there's a 16% change. It's not really significant, okay? And actually in this particular location, we measured and estimated that fall was reducing, that spring lost more than fall. In this time frame, we measured that fall actually lost less than spring. When you say, okay, what if you add cover crops to a spring system? There's a 57% reduction in the amount of nitrogen leaving the tile. If you add cover crops to a fall system, 40% reduction. If you say, okay, I'm gonna move my nitrogen to the spring, and another farmer says, well, I'm gonna leave my nitrogen in the fall and add cover crops, there was a 50% reduction. Okay, when you had fall cover crops versus spring in without cover crops. Okay, when you look at spring in with cover crops versus fall in with cover crops, about equal. And you can see that here. They're about equal, they're the same. So that tells me that despite when I add the greater portion of the nitrogen in the split, in the application split, when I add cover crops to the system, I'm getting a drastic reduction in what's leaving the actual tile. And it's being done by taking up nitrogen and assimilating it in the structure of the cover crop. And also, because that cover crop is transpiring and transevaporation is occurring, it's reducing the amount of water that's leaving the field. When you combine those, you get drastic reductions in nitrogen loss. Now, this blue line is the zero control. Does anybody see something wrong there? Does anybody see something wrong with that? Is something abnormal there? Would you expect, if you didn't add nitrogen, to have the greatest loss over the time period of the study? No. So, what's happening? Mineralization, very good. 3.5% organic matter on average in this field. You have a corn plant that's not being fed properly, its ability to put a demand on the water and to put a demand on the nutrients that are in the soil solution is really low compared to a healthy plant that's been fertilized properly, right? So there was no demand really on those nutrients in solution. So they hang out in solution, and if they're hanging out solution, they can move, okay? Number two, when you think about the fact that there was no cover crop here in this system also. So in the fallow period, during the winter, there was no demand on those nutrients, okay? So when you combine that with good organic matter, you get equal or greater loss. I would call that equal loss of nitrogen, even when you're not applying any nitrogen. And that's what some of the people who have opinions about nutrient loss from the Midwest don't seem to really get. Now, does this get better or worse if climate is changing? Does it get better or worse? It gets worse. So, we need to have some management that that can be applied to bring this also down, to reduce that loss. When you think about nitrogen cycling, what we found was that the cover crops took up or had within its structure 3 times the amount of nitrogen that it prevented from leaving the tile. That's a hard concept to get. That radish, that cereal radish, had within its structure a mass 3 times the mass of nitrogen that it prevented from going to the tile. So that means that we were able to measure the difference. Let me just do this. Let's just take, if we took the average here and we took this number and we subtracted, and then we subtracted that from what was in the cover crop, you came out with 3 times more of what was in the cover crop compared to what it prevented from leaving the tile. What does that say? That means that we are getting nutrient cycling. We're taking nutrients that would normally be lost, putting it back into the system, and it's feeding soil health, right? And it's going into the organic matter. And there's a surplus. That means that it's building over time. So in 5 years, I'm going to do a soil health test. And I'm going to expect to see more respiration of microbes, more organic nitrogen, total nitrogen, more carbon, which those two make up organic matter, so more organic matter. I'm expecting to see that. If I don't see that, I'll be really, really surprised. My longest long-term project, wherever I had cereal, I got a 0.5% increase in organic matter in a 5 to 6 year period. So I'm expected to see something similar here, okay? So we are cycling. We're cycling. This is just a graph showing you flow-weighted concentrations, and this is this spring of 2017. And I just want to show you this. You can see cover crops are really impacting the nitrogen that's lost despite what the flow rates were, okay? And then the zero control is that red, those red dots. Seasonal nitrogen impacts, which looks just like the effect of cover crops on the water that was leaving the field. The green bars represent cover crops. Whenever there was a cover crop growing season, we had reductions. Some of that reduction carry over into the soybean growing season because in between the two, there's no nitrogen application. But if this was corn, like you see here, there's a nitrogen application here, and so you don't get the effect of the cover crop. So that means that cover crops are effective while they're living in reducing what's leaving the tile. And they're making such a big impact while they're living, when you get to December and you look at your annual loss, there's a reduction. But we can make a greater reduction if we were better while the corn was growing. You see that? Then we could couple the practices to get a greater combined impact on nutrient loss, okay? Dissolved reactive phosphorus, same trend. When the cover crops are growing, they're reducing the amount of phosphorus leaving the system. Is phosphorus a part of organic matter? Yes, because it's in proteins. You see how this is feeding back? And we're also cycling phosphorus. Haven't done the calculations yet, but I'm pretty sure that this system is cycling phosphorus, okay? Now this is another one of my favorite slides. So this slide is analyzing the loss of residual nitrogen. So corn year, soybean year. This is the loss of nitrogen through the tile, pounds per acre in the corn year. This is the loss in the following soybean year. This is for a spring system without cover crops. Fall system without cover crops, it's about equal, okay? But when you add cover crops coming out of corn, cover crop, and then soybeans, in the spring system, you get a 64% loss, a reduction of the loss of the nitrogen that's residual. So this is nitrogen that the corn did not take up the previous year. In the fall system, you get a 57% reduction in residual nitrogen loss. What is the percentage of nitrogen that's taken up by corn that was applied as fertilizer on average? Does anybody have that number in their head? So if you apply 100 pounds, how many pounds would the corn actually take up? About half. So that means the other half, the other 50 pounds, is in solution, either getting absorbed by microbes, and if you don't have a cover crop, it's not being absorbed, it's waiting to be what? Lost. But when you add a cover crop, you can affect that loss, you can reduce that loss, okay? So now, here's a money slide. This is the yield from this system. So you've seen the environmental benefits. We're doing really well so far. The treatments are displaying or indicating to me that cover crops are having a big environmental impact. Now, agronomically, I think that we can get much better. I'm just being honest based on the data. So when you look at soybeans, there's really not a significant difference in yield. Soybeans are fine, right? But when you look at corn, that 2015 corn, there is some differences occurring, and the differences are coming when you add cover crops to the system, okay? So for instance, there's no difference in the fall system. With or without cover crops, exactly the same, and they were equal to the spring system. But when you add cover crops to the spring system, and we got the side dress on late, because that June and July were record high rainfall in Illinois. Okay, especially that June. So we were late getting the nitrogen on, and I think that hurt us. And we got a slight yield reduction. But now look at the zero control. I know someone was thinking, you don't know what he's doing, he did design that project right. That nitrogen is bleeding over to the zero control and causing that loss to be that high. That's what I thought too. But when I saw the N uptake, and when I saw the yield, and saw the drastic reduction in yield, then I knew that those corn plants were actually starving and were not really getting any nitrogen. So what we were seeing was real, okay? So I had a graduate student to do his master's thesis by trying to quantify the impact of just the environmental benefits of the cover crops, and to see if that alone would affect the cost of the cover crops, the cost of implementing the cover crops. So in other words, we wanted to know if we just look at the environmental benefit of cover crops, how much of the cost would that pay for? Okay? And so we had to look at, it was a case study. So this farmer was gracious. We got everything that he did, how many trips across the field, maintenance on equipment, everything that you can think of, we basically quantified it. And then we looked at the yield. And then we looked at the cost of implementing the cover crops, the seed, the application, all of that is included. And to summarize, this is what we came up with. And this is only across 2 years, so a corn year and a soybean year, but we cover crop after each. So basically, we found that cover crops, just the environmental benefits, have the ability, on average, across all of those treatments, to account for about 61% of the cost. Just the environmental benefits. Now, what was influencing that cost recovery? So he found that basically, number one, cover crop biomass mineralization offsets 19 to 60% of the initial cost to establish. Nitrogen loading reduction, reducing nitrogen from leaving the field, accounted for 4 to 40% of the initial cost to establish the cover crop. We did a model to determine the impact of cover crops on reducing soil erosion, and that only accounted for 4 to 7% of the initial cost of establishing the cover crops. Why? Because we were on 0 to 2% slope, so there was not a lot of erosion. But we did get very good nitrogen uptake, and from studies, we were able to, and I'm gonna show you some of this data, we were able to predict estimate when that nitrogen that was taken up by the cover crop would be released and how much of it. And so from a couple years of study, we found that about 80 to 90% of what was taken up will be available in solution, just like if you were adding fertilizer. So we accounted for that, okay? Now, we're not saying that it will be taken up by the crop. All we're saying is that when decomposition occurs, it will be in solution available to that year's crop. That's all we're saying, okay? Then second, we said, okay, how much did it cost per pound for the fertilizer to be added? And we took that cost and basically associated it with the pounds of nitrogen that did not get to the tile and was lost. And that's how we came up with this cost recovery. Okay? So that's the economics of things on a field/plot scale. And this is just the environmental. So why do you see this variation? Does anybody know? It's because of yield. If the yield was equal, then we would be on the higher side on each one of these. This is the fall system. This is the spring system. The spring system had the largest yield reduction associated to cover crops. Now, we're also studying how to make yield equal or greater when you have an inclusion of cereal in the cover crop mixture before corn. And I know people are going to say, you'll never get there. That's not a good thing to do. I know, but cereal is the workhorse cover crop of the Midwest. If we can understand how to make cereal profitable for farmers, then we can solve a lot of problems, because it just makes things dummy proof, right? Oh, I'm late. I didn't get my seed in on time. You throw it in October. In the spring, it's green as day. You know, it covers up for mistakes. And it's still going to grab you at least 30 pounds of nitrogen, even if there's no DAP or nothing applied, just from residual, right? So basically, I have a student who is optimizing nitrogen application starter rates whenever you have corn coming after cereal. He's going to do that across the state, 2 or 3 places across the state, so north, central, and south, okay? And we're going to try to optimize that over a 2-year period, 2 to 3 year period. And if we can come up with a starter rate, because I believe that cereal has a higher C/N ratio, and so it's going to slow down the nitrogen cycle and cause some nitrogen immobilization to occur. But if I can offset that with an addition of starter fertilizer and still get equal or greater yield, then the environmental benefits would help, and equal yield would help cover crop cereal pay for itself. And plus, just adjusting some of the rates of the cereal application. So we already summarized. So now this next study is basically a watershed concept. So we're not talking about 1.6 acres, but we're talking about 570 acres of cover crops in one spot in a watershed. This is in also in Illinois, in the town of Towanda, right off of I-55. Okay, so we identified 2 watersheds, and these 2 watersheds contribute to Lake Bloomington, which then supplies the drinking water to the town of Bloomington, Illinois, and to the village of Towanda. Now, this watershed is notorious for being EPA impaired for nitrogen, sediment, and phosphorus. So if you wanted to see if cover crops can do something on a watershed scale, this is one of the hot spots to check it, okay? So there's watersheds of 2 different sizes. The non-cover crop watershed is about 770 acres. The cover crop watershed was about 1,100 acres, And at each point of these red points, this watershed is draining into Money Creek, which goes to Lake Bloomington. And at each one of those points, we're automatically taking samples depending on the flow rate, okay, to try to see if cover crops is having an effect. Now, we cover cropped 48% of that larger watershed. Going on 2 years in a row, we've gotten very good stands. We're flying it on. That's just how the farmer would have to do it. That much acreage, 567 acres at one time. That 567 acres is managed by 6 farmers. And it was amazing to me to find that the farmers, I didn't pressure them to select a certain cover crop. The one portion of this is to see if money was not an issue, would farmers adopt? And almost 50% of them did. And then the other thought was, what would they adopt based on the training that we've been giving as extension agents over the years? And they did a good job. Somehow they got together. I met with them individually, but they all said the same thing. They said, before before soybeans, I want cereal rye, and before corn, I want radish oats, right? And so I did exactly what they asked me to do. I adopted that for them, I got it applied, and basically, in 15, there was a lot of soybeans that were going to be in that growing season. So in the fall of 15, this is what the fly pattern looks like. We were dominant cereal rye radish, and only maybe 20% of the watershed was radish oats. The next year, one farmer said, the largest farmer, said, you know what, scratch that. I want to go annual rye radish before my corn. And so I had to do what he said. So that's why you see a third color. This is the annual rye radish on 360 acres. And then the rest was cereal rye radish, the yellow, and then, radish oats, the yellow before corn, and then here's the soybean where you had cereal rye radish before the soybeans. This is kind of what it looks like from the aerial view. That's what it looks like on the ground. Now this is throwing it out of airplane, right? On over 500 acres. This is that 360 acre field here. So we're going from one acre to hundreds of acres to try to see if the impact of cover crops is the same. Because if we can't do this, then what we're doing on a plot scale is not worth it. Because we're going to affect the Mississippi River Basin and the dead zone by doing this. Not by farmer A and farmer Z, only people cover cropping in the watershed, or only people doing anything about nutrient management in the watershed. That's not how it's going to work. So I like to throw this picture in. Does anybody see a problem there? Big problem? What do you see? Brad, what do you see? Okay. Why? That's right. So what we had radish oats. And how does an oat plant grow when it gets excited? Does it grow like this? It grows like that, right? Now, how do we harvest soybeans? Like that, right? And so we were giving the oats a haircut, and we were harvesting the soybeans at the same time. And out of the back end of the combine came green oat residue, okay? So the question was, so when he sent me this picture in a text message with a whole bunch of question marks saying, what the hell is going on? That is about 80 acres. He almost hated me. I said, you know what? I was prepared for emergencies. I got a pool of money. Just go ahead and finish. Continue to take pictures. Take it to the elevator. Let's see how much chaff you have. Let's see what happens. Went to the elevator, and there was no effect. No effect. So then I got another text message with the same picture, and he said, I'm so proud of the cover crop growth here. I said, wow, what a change in attitude, right? So it turns out that there was no effect here on what he was harvesting. Harvester did a good job. There was basically no effect. But these things happen and it looks ugly. But unless you go through them, you won't know if they're hurt or not. That's why I like to throw this up here. So it's not perfect. So across that 500 or so acres, we got brave and we said, you know what? We're going to go out and do a grid sampling of the biomass across 500 acres. I didn't do that. My graduate did it. That's my guy, Richard Roth. He went out, GPS, gridded points across the watershed, collected biomass, and we determined percent in, because I wanted to know what's the variability of the growth and the biomass. So I'm used to looking at things, 2 acres, 5 acres, but now we're talking about 500 acres. Is the variation big, small? What is it compared to a plot scale? And so this is what we got. You can see the variation here. This is in pounds per acre of biomass. You can see the variation, right? And so basically he found that cereal radish competed the radish oats, and this is total biomass. It was significantly different, 1,500 pounds per acre versus radish oats that was just 409 pounds per acre. Now that's the power of having that mixture. Something that grows in the fall very rapidly, then mix it with something that grows in the spring too. So the difference from fall to spring was 1,120 pounds per acre of biomass. That's huge. That's all the cereal doing that. So what's the associated in uptake? Significantly more in uptake in the, by cereal radish compared to radish oats, right? And the change from fall to spring was 38 pounds per acre. That's huge, okay? That's because the cereal kept growing. The next year, I told you we had this guy who threw in the annual ride at the last minute. He actually should have stuck with his first thought. He would have got this, but he ended up getting 473 pounds per acre biomass. Now this is just above ground. We did not get crazy enough to, at each point, grab the roots too. And plus the farmers didn't want the holes in the fields, every couple or so acres. So radish oats, cereal were about the same, and they were both significantly different than annual rye. And look at the in uptake difference. It's always going to follow the biomass. They're about the same, 49, 42 pounds per acre compared to 22, right? And you can see the variation across the field. A lot of variation there. So we can't make estimates so easily by looking at a plot to say this is going to happen like this the same way on a watershed. We just can't do it. Too much variation. So we got even braver. We said we're going to take soil samples across 500 acres like this and try to correlate it with the biomass. So we took the soil samples, and you can see the variation in the nitrogen nitrate in the first foot, and we wanted to see if the cover crops were affecting the nitrogen concentration in the first foot of soil. We saw some effects where you were going into soybeans and you didn't have a nitrogen application. We saw an effect where cereal increased the amount of ammonium compared to where you were going into soybeans without the cereal. But then where you were going into corn, the system was flooded with the nitrogen application. 50% of it in this watershed was fall applied. And then, so we couldn't see the spring application. So the application of inorganic fertilizer in the fall kind of dominated the system, and we couldn't detect the difference that the cover crop was making. And the same thing for the next year, you saw a similar trend. So that was biomass, uptake, and soil. So what's happening with the water? That's what this is showing. Discharge. Now what do we see on a plot scale? We saw that when the cover crops were growing, that less water was leaving the tile, right? Now we're on a watershed scale. That first year, basically the treated watershed, the cover crop was about equal but slightly greater than the reference watershed. Then things were really close together during the time when the cash crops were growing. Then you come to when that watershed, watch this, was dominantly soybeans. That going into the next growing season is going to be dominantly soybeans. So you didn't have much nitrogen being applied in that fall. So basically, you did see an effect of the cover crops on the discharge. Whenever there was a huge storm, you got less flow from the tile when you had cover crops. That's the same thing that we were seeing on a plot scale. Let's fast forward to nitrate loss, okay? So in this year, this is the cover crop season that's following a cash crop season where it was dominantly 60% corn. So you had way more nitrogen applied in this year. So the cover crops had more work to do here compared to here, okay? Because this growing season was dominantly soybeans. So less nitrogen applied, right? 60% of the watershed is soybeans, and you saw a bigger effect because there was just less nitrogen in the system. On a watershed scale, you're talking about 1,100 acres, and we only cover crop 50% of that, but yet the water that's coming out is being affected by only cover cropping 50%. There's less nitrogen during the larger storms that's leaving the field. So we are seeing an effect of cover crops, and I've already summarized. Last study, okay? This is the release study, okay? So when you look at this field, this is cereal rye in the spring. How much nitrogen do you think is here? No, wait, forget about how much nitrogen. Let's say you had 40 pounds per acre in this biomass. What percentage of it is going to be decomposed and available for the corn that's growing after this, or the soybean that's growing after this? What percentage? Do I hear 30%? 30, I got one at 30. Do I hear 40? Nobody, 50%. Got one at 50, two or three, 60, 70, 80. Got two at 80. Let's see what happens. So to study that, we actually had to go out, take the biomass, remove all of the corn residue, and put back just the cover crop biomass into the field, and then measure that over time. And this is what it looks like. So the treatments were cereal rye, no-till, cereal rye, light spring-till. Okay? Harry vetch, no-till, Harry vetch, light spring-till. So you're talking about finisher and then plant. This is the 50% line. This is the percent carbon remaining. So this is showing decomposition. So you get to about 50% decomposition at when we think the plant is at V5 to V6 in that subsequent growing season after termination. Okay? You get there faster when you have tillage. You get there slower when there's no till. At VT, this is a critical point, you had a range of 50, about 30 to about 10% left in the plant to decompose, so left in the residue to decompose. And then at R6, you had about 5% left to decompose. So most of that, of both decomposed, okay, within the growing season of the corn plant. Very good. I'm going to show that in 2 slides. It's about 16-to-1 for the cereal rye mixture, and for the Harry vetch, it's about, I think, 10. And I killed it before the boot stage. This is the nitrogen percent nitrogen released. So this is the 50% line. It's safe to say that everything but the cereal rye no-till released over 50% of its nitrogen from the residue before V6. The no-till cereal got to that point between V6 and VT. At VT, everything was definitely greater than 50% release. So that means that the decomposition occurred and the nitrogen was either in the ammonium or the nitrate form in solution. Now, that does not mean that that nitrogen went directly into the corn plant because it has to get processed by the microbes first. And depending on the CNN ratio, that process will take slower or it may go faster. Okay, so we're trying to track that too. By the end of the season, let's say when the plant stops taking up nutrients, the amount released is, about 90%, over 90% for all of the treatments. But again, the no-till treatments got there slower compared to the treatments where you had like spring tillage. CNN ratio, that answers your question. At termination, you're starting at about 12 to 1 for both of the hairy veg plots, and 14 to close to 16 to 1 for the cereal. Now notice the trend for the hairy veg is flat, and the trend of changing CNN ratio for the cereal treatments is linear, decreasing with time. Watch this. The slope or the way that this line is projected, whether flat or on a linear decrease, tells you or indicates how hard the soil microbial community in the soil has to work to use that nitrogen or to make that nitrogen free and available. You get that? So for the hairy veg, whether till or no-till, because it's such a light material, there's not a lot of work to do. So you don't see that line changing much. So immediately, nitrogen is available. But for the cereal, whether till or no-till, you see this slope, this heavy slope? That means that until it gets to about 12 to 1, that system is working overtime. So it's an indication that there was some immobilization occurring. Now, if I was to add starter fertilizer here, or whenever we plant it, then I can flatten this line out for the cereal faster. That means that the system would process faster because there will be more nitrogen there, so the C to N ratio would be lower, microbes will be happier, more efficient, and the corn crop will be happier also because the pool of nitrogen will be larger that's available for its roots to take up. Okay? And so that's my last slide. Here's my information. We do have some things on YouTube, and if you just want to email and ask a question, I'm open to answer questions by email and to answer a couple now if I do have time. Thank you for being a good audience. Any questions? Okay. Only on the fall in that study. But in the watershed study, I had no control. It could be an effect, but most farmers in that region, they wouldn't add N-Serve to a spring application of nitrogen because they want it to be available fast.
You say spring application, you use herbicide rest. So spring application, post-plant or pre-plant?
Post-plant at side dress, yes. So 80% of the nitrogen in that treatment of the spring-dominated split went down at side dress, and 20% went down in the fall as DAP. So I asked the farmer to count that DAP application. Nothing on the planter. That's where we're moving. So we wanted to start basic, conventional, worst-case scenario, especially cereal before corn, and in a corn system at the first 2 years. So now, after we've learned what we can do and how the system reacts according to our current treatments, now we want to infuse the management of adding some starters. So we're going to make a 3-way split and see how that changes the system and if we can get more of the cover crop to pay for itself with equal or greater yield in the cover crop treatment compared to the control without. So we're kind of moving we're progressing from conventional to more alternative and novel and higher technology management. So we can show a progression over time to farmers. Because in that region, most of the farmers are still with the conventional methods.
So even when we go in here with the starter fertilizer and breaking it down to capture the plant and also the
No, I can't say that because it depends on what Mother Nature does. So let's say, so I think that you're asking if we put more of our nitrogen in the spring, are we less likely to lose? Yeah. Yes. You should get more available nitrogen, and then that means that the plant is not, the corn plant, let's say following cereal rye, with starter added, is less, it doesn't have to wait on the cereal rye to release that nitrogen because it has its nitrogen already there. The microbial system that's driving all of it is more nitrogen rich, and so it's going to go ahead and process the residue of the corn stalks and the cereal rye, while there's still a good pool of nitrogen there for the cash crop, the corn, to continue to grow. So what's happening is, without the starter, because the cereal rye has a chemistry that's heavy carbon, it's causing the microbes to take away nitrogen that would normally be available for that corn. Yes, and so I'm wanting to subsidize the system and add some nitrogen to take away the immobilization and to make both the microbes and the corn happy and see what happens. So to do that, I have to optimize that. So I have to start zero starter, 20 pounds, 60, 70. And then we're going to do 2 by 2 so we can get a higher rate. That's a good question. Yeah.
I was under the understanding that cereal rye had an antagonistic effect on corn. Have you looked at annual ryegrass at all, or do you have any consideration of where that would fit in the cereal rye?
Yeah. To your first comment, I have a colleague, Tom Casper, who did a lot of work on termination dates of cereal rye before corn, and he found that if you are 3 weeks before, if you're 3 weeks before planting with your termination, then you are less likely to have that antagonistic effect. To answer your next question, I'm really sensitive to the farmers where I do my work, so I use people on the ground that sell them fertilizer and so forth to kind of get an idea of what they're using now, because that's going to be the quickest thing that they adopt. They may be using it on the back 80. They may be using it on the side 20, but they're using it already. That means that they have the technology to implement it. So I go with what's in their hand and try to advance that. So in this region, in central Illinois, most farmers are using cereal rye because they're not flying it on. They're coming and they're drilling, and cereal rye allows them to do that because it overwinters. Their experience with annual rye, depending on the variety, I know that, but they were getting sold annual rye varieties that did not overwinter, but it was a promise that it would. So it turned them off from annual rye. Now, I think that annual rye could be productive, but what I've also found on a watershed scale, when that farmer decided to use annual rye, is that annual rye is actually affected by the winter way more than cereal rye, because the change in growth was negative. So that means that annual rye grew well in the fall, but then when the winter hit, it lost some of its biomass and it never recovered it. Whereas cereal rye, you saw the change from fall to spring, it was massive. So it is a consideration if I can get the right genetics, where I can get, I don't want to set them back by introducing a cover crop that does not grow vigorously in the spring, because we need that.
Well, I really applaud your research on that. That's exactly what we need to know. And I think you're exactly right on cereal rye because
policy.
regulatory, or if they see this kind of research, they're going to want to make it possible for the farmer to go to this.
It's hard for me to answer who's looking at it. I know that my funders, by the way, most of the studies you saw are funded by farmers. So in Illinois, there's what you call the Nutrient Loss Reduction, the Nutrient Research and Education Council. And that council made a deal with the farmers that it's a fertilizer checkoff. Every ton of fertilizer, nitrogen fertilizer sold, there's a 75-cent tax that goes toward research. And that generates $2.6 million a year for that state to do nutrient management research. And so all of the regional scientists gets a chance to respond to the request for research, and that's how I got awarded a couple of years in a row, and that's how I was able to fund that. So that agency then advocates to Washington, D.C., based on the data that we as scientists are collecting based on the funding that's coming from farmers. So that says two things to D.C. and EPA. That says, number one, farmers are trying to do this themselves, not by anecdotal research, but by giving funding to those that have that are at the universities and so forth, to really do some replicated, robust, complex studies to figure out the problems, and they're funding it themselves. Number two, they can use some of the data to say, for instance, the climate change issue and the nitrogen mineralization. EPA don't necessarily understand that in the bread basket you have 3 to 4% organic matter where the farmer is responsible and where the parent material allows. So in that, if you just do prairie, you're going to get a lot of loss without commercial ag even touching the soil. So studies like this that have a zero control allows them to go and say, listen, this is done by a university, this is not farmer A and B getting together trying to do this themselves, and they're finding that if I don't touch anything, I'm losing over, above the EPA standard in nitrogen as far as 10 ppms. Also, it says, here are some treatments that we know can work. Can we get some subsidies in order to get this done on a watershed scale? So those two things, what I know is happening, but that's happening from that one state. That's all that I know of. But I'm sure the reports go all over. So the EPA is actually looking at it. I don't know how widely, but they're looking at it. Say it again. It depends on how close you're doing it to planting. If you're doing it where the cash crop, the corn, before corn, can actually see it and use it, it's not a bad thing. It's almost like starter. But if you're doing it early spring, and you get the rain that we got this spring, you're not going to see it. One more? Mm. Okay. First question, I have the samples, but I haven't analyzed for anything other than phosphorus and nitrogen. Second question, I think the cover crops are sequestering some of your cations and possibly sulfur, but I haven't measured it, especially cereal rye. What I'm finding is that radish has the tendency to actually speed up the nitrogen cycle, or speed up decomposition, because it's such a tender, low CNN ratio material that microbes devour it really, really, really fast. Where cereal rye, it slows the system. So if you're building organic matter or your organic chemistry in the soil, you want something that's going to slow the system down. So over a 6-year period, we found that there was a significant increase in extractable phosphorus where you had cereal rye compared to the control and radish. A significant increase in potassium where you had cereal rye compared to control and radish. A a significant increase in organic matter, protein content, and a slight increase in respiration. In other words, the lab takes the soil and puts in sodium hydroxide, and because microbes breathe like us, they let out CO2. They can trap that CO2, and the mass of the CO2 is an indicator of how much respiration is there, and the respiration tells the scientists how many microbes is there. So we're seeing those things. So to answer your question, P and K definitely, I've seen over a 6-year period, cereal rise increasing that. Now, I haven't looked at it with depth to say, is it being stratified, or is there increase lower even with the root decomposing? Because the cations don't move as readily as the nitrate and sulfur and phosphate does. So it could be a whole depth thing, or it could be happening right at the surface. I don't know yet. Type of burn, so time. I'm really aggressive in terminating. I'm not as brave as as Rodney may be. So I normally like to get out there 2 to 3 weeks before planting. Now, if I had a spring like we just had, and it's growing like crazy, and I already have the biomass that I had, March, April, in late March, if I go and sample the biomass, and I know I have the same biomass as I had in all the other years in late March, then I go ahead and terminate. Because if you let that in 11 days, cereal rye in the spring can double its biomass almost. Eileen Kalidifko did that before cereal rye. She had different termination dates, and she found that you can double the biomass in late spring with the heat units that the cereal rye is getting. So I want farmers to get optimum yield, and I know that if there's corn coming behind that cereal rye, there's no way they're going to get that yield unless they're dumping nitrogen in as starter. And I don't know the percentages of farmers using starter in our area.
I think it's pretty high on ones that are using cover crop. We've seen the need.
They're using, yeah. So I hope that 2 to 3 weeks.
Yeah. So, well, I think Chalmar is going to hang around for a while today, right?
Yes.
Okay,
Yes.
great. So he'll be here for a while if you want some more questions. I think we can all see why we were willing to break our university rule and have Chalmar here to speak. I think what he's doing and the advocacy that he's doing for us and the research that we need done is tremendous. So give him a round of applause and thank you for coming today.